Section 7.3, Electric Fields. I want to start, before we begin, to recall gravitational fields. So the force of gravity is calculated by determining the mass of the object and multiplying it by the gravitational field intensity. And G, the gravitational field intensity, the units are newtons per kilogram. Today we're going to look at electric fields. An electric force is equal to Q times epsilon, where Q is the charge in coulombs, and epsilon is the electric field, and its units are, instead of mass in kilograms, are in coulombs, because charge is measured in coulombs. So electric field and the gravitational field are very similar, and the gravitational force and electric force are also very similar. There are many similarities. In fact, whenever we're answering questions, you can always, in the back of your head, remember gravitational fields, something that you have experienced, something that you have practiced and studied for some time now, and you can always compare it to the electric fields. So let's begin. We can describe the electric force between a pair of charges using Coulomb's law. But there's another way to describe electric forces. Suppose there is a single isolated point charge that is far from any other charges. This charge will produce an electric field, a region in which a force is exerted on an electric charge. The electric field is the region in which a force is exerted on an electric charge, the electric force per unit positive charge. And the unit, as I mentioned up above, is newtons per coulomb. We can determine the magnitude of the electric field using the equation K Q2 over R squared, where K is Coulomb's constant, which is 8.99 times 10 to the power of 9 newtons times meters squared per coulomb squared. And R is the distance to this point charge. Now, it's important to note, if Q is positive, then a positive test charge placed near Q or within the electric field will be directed away. So if we have a positive charge and a positive test charge, then they will repel. The field will push them away. Conversely, if Q is negative, then a positive test charge placed within this field will be directed towards it. This is the law of electrostatic repulsion. Saying that like charges repel and opposite charges attract. Okay, let's try a sample problem. We'll look at an electric field due to 2 point charges in one direction. 2 point charges are 45 centimeters apart. That's the total distance between Q1 and Q2. The charge on Q1 is 3.3 times 10 to the power of negative 9 coulombs, and the charge on Q2 is negative 1 times 10 to the power of negative 8 coulombs. Calculate the net electric field at point P, which is this point right here, 27 centimeters from the positive charge on the line connecting the two charges. So we have one positive charge, Q1, and one negative charge, Q2, and we place P 25, or 27 rather, centimeters. That leaves this distance, R2, as 18 centimeters. What we want to do is estimate the field, or calculate the field rather, for charge number 1. It's equal to K Q1 over R1 squared, where K is Coulomb's constant, 8.99 times 10 to the power of 9 newtons times meters squared per Coulomb squared, times Q1, which is 3.3 times 10 to the power of negative 9 coulombs, divided by the distance, which is 0.27 meters squared, or 27 centimeters. If we punch this into our calculator, we get, and I will include a direction in this, 4.07 times 10 to the power of 2 newtons per coulomb. And since P is a positive charge, as it states here, and Q1 is positive, then P will be pushed to the right because of this field. Okay, let's determine the field magnitude for Q2, a distance of R2 squared. If we sub and solve, that's 8.99 times 10 to the power of 9 newtons times meters squared per coulomb squared, times, this time the charge is negative 1.00. I'm going to omit the charge, but we're going to analyze the direction afterwards. Times 10 to the power of negative 8 coulombs divided by, as I mentioned, this is a distance of 18 centimeters squared. And just verify that subtraction. Yes, that was correct. No shame in double checking. Punch this into your calculator. You end up with a magnitude of 2.78 times 10 to the power of 3 newtons per coulomb. Now let's analyze the direction. P is positive and Q is negative, and that's going to drive this force towards it, so the field will be pushing it to the right. And this is the field at point 2. Let's find the net electric field. It's equal to the electric field at point 1 plus the electric field at point 2. It's 4.07 times 10 to the power of 2 newtons per coulomb. To the right, plus 2.78 times 10 to the power of 3 newtons per coulomb. To the right. Since they are both in the same direction, we can add them algebraically. If we do so, we end up with 3.2 times 10 to the power of 3 newtons per coulomb right. And there's our statement. The net electric field is 3.2 times 10 to the power of 3 newtons per coulomb to the right of point P. In part B, we're going to place a new charge of 2.0 times 10 to the power of negative 12 coulombs at point P and determine the electric force on this new charge. So we want the electric force, the net electric force, which is equal to this new charge, Q, times the net electric field, which we just calculated. So this new charge is plus 2.0 times 10 to the power of negative 12 coulombs. And the net electric field that we calculated was 3.2 times 10 to the power of 3 newtons right, newtons per coulomb right. Punch this into our calculator, we get 6.4 times 10 to the power of negative 9 newtons, again, direction right. Therefore, the electric force acting on the new charge at point P is 6.4 times 10 to the power of negative 9 newtons to the right of point P. Okay. In sample problem number 2, we are going to look at the electric field due to 2-point charges, this time in 2 dimensions. So Q1 is along the y-axis. So let's find the electric field in the y direction for Q1. And Q2 is in the x direction. Let's find the electric field in the x direction for Q2. Q1 is 4.0 times 10 to the power of negative 6 coulombs. And Q2 is negative 2 times 10 to the power of negative 6 coulombs. R is 3 centimeters. So let's find electric field at y, electric field at x. Starting with y, it's K Q1 over R squared. K is Coulomb's constant. Q is 4 times 10 to the power of negative 6 coulombs divided by 0.030 meters. That's 3 centimeters squared. If we punch this into our calculator, we end up with 4.00 times 10 to the power of 7 newtons per coulomb. Good. We'll do the same for x. It's K, this time Q2 over R squared. Again, 8.99 times 10 to the power of 9 newtons times meter squared per coulomb squared times this time the magnitude of the charge is 2.0 times 10 to the power of negative 6 coulombs, and divide this with a radius of 0.030 meters. Don't forget to square it. If you do so, you end up with 2 times 10 to the power of 7 newtons per coulomb. Okay. So we have one electric field in this direction, the y direction, and one electric field in the x direction. And we can find the net electric field, the magnitude of it, by using Pythagorean theorem. They're not asking us for direction. So it's equal to EY squared plus EX squared. It's equal to the square root of 4 times 10 to the power of 7 newtons per coulomb squared plus 2 times 10 to the power of 7 newtons per coulomb squared. If we punch it in, you should get 4.5 times 10 to the power of 7 newtons per coulomb. There you go. Therefore, the magnitude of the net electric field at the origin is 4.5 times 10 to the power of 7 newtons per coulomb. Now let's spend some time looking at electric field lines. An electric field exists in a region around a charge. So we have a diagram showing a positive charge, and we have these electric field lines, which are directed line segments pointing away from the positive charge. And in part B, we have a negative charge, and we have the electric field lines, which are directed line segments, pointing towards the negative charge. The field and its the properties can be represented with electric field lines. They can help us determine the direction of the force on a nearby test charge. If the charge is positive, then the electric field lines are directed outward, away from the charge. If the charge is negative, the electric field lines are directed inward. So positive outward, negative inward. Good. The gravitational force lines from a mass m spread out as r increases, the radius or the distance increases in all directions. The electric field lines from a charge q also spread out in all directions. So here we're comparing gravitational field lines and electric field lines. So here we have gravitational, and here we have electric. So they're very, very analogous. The farther away you are from a charge, the smaller the force is going to be. These field lines spread out. The closer they are together, both types of field lines pass through larger spherical surface areas as at greater distances. The surface areas, A, over which the field acts, increases as r squared increases. So the field lines themselves exert an inverse square forces. So how do 2 point charges that interact through Coulomb's law know about each other? In other words, how does one charge transmit electric force to another charge? In terms of electric field lines, every charge generates or carries with it an electric field through which the electric force is transmitted. Let's look at electric dipoles. An electric dipole is a pair of equal and opposite charges with centers separated by a small distance. So in this diagram, we have Q, a negative charge, and positive Q, a positive charge. And you can see that the lines for the negative charge are directed towards Q, and for the positive charge are directed away from Q. If we were to place these two charges beside each other, we would end up with an electric dipole. And if you take a look, the direction in which these field lines are pointing is from the positive to the negative. The two charges in an electric dipole give rise to a more complicated electric field than the one associated with a single charge. As the field extends into space around the other charge, they interact with each other, producing field lines that bend towards the other charge. Notice that along the vertical axis, midway between the two charges, the field line is parallel to the line connecting to them. So we're looking at this line right here. It is parallel to the line that is connecting them. This remains true along the vertical axis at all distances from the dipole, although the magnitude of the electric field decreases at distances that are farther from the dipole. The direction of this electric field always points, as I mentioned, from positive to negative. Although the field lines of a dipole merge at the midpoint, the field lines do not cross. What happens if we have two like charges? So here we have a positive charge and a positive charge. The illustration shows how they appear in a plane. Note that the electric field is zero along the line that bisects the line connecting the two charges. If this were a math class, we'd call this an asymptote. The electric field line at that particular point is zero, and these are repelling each other. They're extending because they're positive away from the charge, but also away from each other. Let's consider the electric field lines around a dipole consisting of 2 plus 2q and negative q. The number of lines from the larger charge is twice the number of lines from the smaller charge. Half of these lines extend from the positive charge to the negative charge. So again, we're going from positive to negative. But the pattern is much different now because the positive charge is twice as big as the negative charge. The other half extend outward as if there was only one charge. These guys are acting as if there's only one charge. They're almost unaffected by this much smaller negative charge. And the last type of electric field is a uniform one. So we have a positive plate and a negative plate, and they will produce an electric field line, again directing from positive to negative. The electric field between two parallel plates or parallel conducting plates is uniform in direction and magnitude, except near the edges, and you can see this. The magnitude of the electric field depends on the amount of charge, the area of the plates, and the materials between them. The electric field outside the parallel plates is zero. Okay, so for homework you have a couple of things you need to do. First, you need to explain applications of electric field lines. In particular, I want you to read the textbook, sections pertaining to electrostatic precipitators, which you've studied in grade 9 and grade 11, as well as what electric field lines have to do with the hammerhead shark. Then try practice problems on page 337 and review questions on page 345.